Noise filtering, digital noise filtering, makes a couple of assumptions about the nature of the noise. It assumes that the noise is, in most cases, the assumption is that the noise is zero mean. In other words, that if I average together a couple of these noisy signals, they'll tend to average out. None of the filters that we're talking about today have the ability to recover the original signal in the presence of a systematic error. And so many of these filters are based on this idea that as long as you kind of just average out a certain window of signals, you'll tend to get something that is closer to the true signal, and understand that that only happens if the error has an equal chance of going high and going low. If it's mostly high, you'll end up measuring a signal that's legit just all the time too high, even if you filter it out. Okay, but this idea of kind of randomly distributed noise, normally distributed noise, is the most common kind of noise that you will ever encounter, because most of the sources of noise are random in this way. And when you add lots of random signals together, you get a standard normal distribution. You should have done this in stats. It's called the central limit theorem. So it doesn't matter how the noise is distributed, you end up, when you average lots of things together, you end up with a normally distributed noise. And which is why you'll see me many times constructing my noise signals using normally distributed noise signal. And so what I've done is I've just taken a normal second order response, and I have artificially added some normally distributed noise. You've seen this kind of stuff before. And in a certain way, you can imagine that there's this whole other problem, which is, given noisy measurements of a data source, how do I get back the original pristine data source? Now, why I spoke about this whole latency accuracy problem is that, again, we face a very different kind of problem when we are working online. In other words, where we only have, at any given time, measurements that are in the past of the measurement of the time where we are at now. And when we have the full spreadsheet and we've already done the experiment, and we can actually use the entire signal in order to reconstruct the signal. Those are very different situations. In control, when we are using an online control loop, because remember that a control loop would be taking this signal, making some kind of control decision, and then manipulating the manipulated variables, right? So that's in the loop. It wants the most recent information possible, but it can't wait. It can't wait. Let's just wait for the signal to kind of reveal itself, and then I'll act on old information. That's not an option. And so you have to understand that we encounter filtering in these two very discrete contexts. We encounter filtering in an offline context, where most of you will have encountered this before. Almost none of you have ever tried to do real-time filtering. Because if you've done CLB and you've taken sampled signals, what you have in front of you when you open that spreadsheet is a full experimental result that has perhaps been, which has been sampled and perhaps been infected by some noise or affected by some noise, and your job or your target is to get back the original signal, right? Now, what kinds of strategies can we use in order to actually reconstruct that original signal from the noisy sampled signal? You'll see that the textbook has a couple of suggestions. The most common version of this is a simple moving average filter. This is so common that it's built into Excel. And so we've got our T, Y, and YM. And if I just select that all, no time for that, let me just do this. So there's our data. That should be a XY scatter. There you go. So there we have our data now reconstructed in Excel. And the way that we would do kind of moving average filters on this is by adding a trend line. And you'll see that there's a trend line which gives me a moving average of a certain period. And so as I increase the period, I get smoother data. But I want you to understand, or at least notice, that as the period increases, this thing happens that I spoke of. The latency increases. In other words, that filtered value is now smooth, but it doesn't actually line up with the original data. If I were to just calculate at any given time, the error, I'd actually be making a larger error. Right, so this moving average filter has made the signal smoother, but it has actually made the signal that I'm working with less like, or in terms of at the moment in time, less like the original signal than the noisy signal. Is this making sense to everybody? You agree with me, right? Because I've got this consistent error. Here, I've got random error, so the errors are kind of canceling out, right? Here, I am always below. In that whole section there, I'm always below the true signal. Right, so I'm consistently reporting a lower value. And if you were to calculate the mean error there, or if you were to calculate something like the integral of the error, right? During this entire time, the integral of the error would just be getting bigger and bigger in magnitude. Whereas if I were trying to do the same thing with the noisy signal, it would move up and down, but on average, I'd be reporting kind of a similar value than before. This idea of doing moving averages is so common that Pandas has built-in support for doing these rolling windows. It basically involves taking this dot rolling. And so let me just show you what that actually looks like if you do these separately. So if you take measured in this case, right, so I've defined measured over there, and that's what the measured signal looks like. It's a Pandas series, so it has a time axis and it has the values that you're talking about, and that produces a rolling window. And the rolling window idea is that we're taking 10 elements at a time, and we're shifting that box over the signal. If I wanted to construct that rolling average like manually, I could say I could count down. I would say, right, those are 10 elements, right? And so here I would just say average of these units, right? And so that average is being calculated based on those 10 numbers. To get the next one down, I could just copy and paste that formula down. And that new sum over there would be referencing those 10 units. And so we're moving this box of 10 across the signal from top to bottom. Okay, and that's the rolling idea. So we're rolling this kind of fixed window across the signal. Now, a necessary consequence of this, and I think that because of the way that we're calculating the averages, we can only really report a 10-element moving average after 10 sampling intervals. Now, there's ways around this, right? We can kind of grow the window, so we can start reporting the first signal and then like do a 2-element rolling average for the second one and a 3 and so on, and then kind of reach up to 10 and go on from there. But the first full 10-element rolling average requires 10 elements to average. And so typically you kind of report late, right? And that lateness continues when we think about what those signals look like. So what I've done here is I've plotted the rolling average for lots of different window sizes, well, for 3 different window sizes, 5, 10, and 20. And what you can notice is as the window size gets longer, kind of predictably the noise gets less or the signals get smoother. I think that's the more accurate expression of what we're seeing. We're not necessarily seeing a more accurate signal, we're just seeing a smoother signal. So the wider your window is, the less crazy the movement will be. And effectively that will have the effect of kind of averaging out. If there's very quickly varying noise like I have here, it'll get averaged out. But you can see here with the 20, so there's 2 things I want you to notice. The first one is that each of these signals is starting slightly later, right? So the 5 window average is starting only at the 5th sampling interval, the 10 window average is starting only at the 10th, and the 21 is starting at the 20th. And so if I have short signals, the rolling average isn't very useful because if I don't have enough samples to fill that window, I won't be able to report a value at all. It means that necessarily a rolling average has that much latency guaranteed. right? Because I always have to wait at least the window size of the sampling to fill the window before I can report my first value. And if these were, let's say I'm trying to sample every second, if I'm sampling every second, that means I start the event, time 0 starts, and I only see my first result at the 10-second mark. So I have to wait 10 seconds before I even see the first number, okay? But it gets worse than that, because even when I start reporting numbers, I also report those numbers in a way that shifts them in time. And so what you can see, I want you to notice two very important characteristics of this slope over here. Firstly, the short window matches the slope very well of the original signal, okay? And it is delayed not by that much. Notice that as I increase the window length, not only does it seem as though the thing is delayed, it's also getting the slope wrong. It doesn't match. The slopes don't actually match. And you should probably have been able to predict this if you think about effectively these things being like high-order filters or high-order transfer functions. And you've seen this before. If I have a step input, a first-order transfer function has a kind of a slope on that step input, right? So it doesn't get the slope 100% right. And if I put another filter in after that, and another filter after that, and another filter after that, every time I have another filter, the slope actually gets shallower. And this is a general effect of all of these kinds of filters, that as we increase the amount of filtering, not only do we filter out the noise, but we also actually start changing fundamental characteristics of the original signal. And so you have to be aware that it's not a free thing. Filtering is not something that you do always. As I've mentioned many times before, these strong techniques, the story that you want to hear is like, here's the magic box, right? You take the bad signal, you put it into the magic box, you get a good signal out. Unfortunately, this box does not exist. That magic box that just always does the right thing and always takes out only the bad stuff and leaves all the good stuff, like you can't build a machine like that. So you have to understand that if you attenuate noise, you're also going to start getting less sharp responses on all of the signals. And you may actually be confused about what is actually happening. Right, so not in the textbook. So this is the version of the moving average that's in the textbook. The actual implementation is exactly like this. If I were to actually copy this down, I should actually get exactly the same result as I got on my moving average plot. So let's just call these 0. Oh, there you go, actually. Yeah, you know you can do that, right? So if you select a piece of the cell on Excel and then you paste on a graph, like it'll add that as a series on the graph. This changes everything. So except for the interesting, like half interesting reveal now, what you're supposed to be seeing is that those lines are 100% on top of one another. So I'm not lying, right? Like that's literally all that trend line is doing. It just is a more convenient form. Why it's useful to be able to implement this in the spreadsheet is because Excel does not have a checkbox for the next thing that I'm going to show you, which is that because we know that these moving averages tend to shift the results up by a certain amount, it can be useful to use the middle of the window to report the value at the center of the window rather than at the end of the window. Is this making sense to everybody? So let me show you what that looks like in Excel first. So remember how we got this formula, right? We put that formula was I was averaging 10 elements in Excel and I was reporting that value at the end of the window. So the time associated with this value over here is the 10th sampling time. But let me show you a different way On a window like this, actually, you need an uneven number, but I'm just gonna fudge it a bit. So this strategy works the best if you have an uneven number of time steps, because then you can report it exactly in the middle. I'm just going to report it like one below the middle. But I can still take the average of 10, but I can take the average of those 10. But I can report it there. Now, there's two important things that I want you to understand about this. The first is that this is not the same as taking that and simply, it's not the same as shifting the signal directly, right? It's not the same as the original one, like moved back. It's just that one calculated in a whole different way. Right? We're reporting at a different part of the window. And what you can see is that this has much less of what is called phase lag. In other words, it isn't introducing this delay in the signal. And as a general rule, these central windowed functions will get a much better fix in terms of the actual time. If I compare just by subtracting them and maybe calculating an integral of the square or something, if I kind of compare the accuracy of approximation of these signals, you can see that the central moving average does a much better job at getting the time at which things happen right. Now, why would I ever use a lagging moving average instead of a central moving average? If the central moving average is obviously so much better, why would I use a lagging one? Why would the textbook even not even mention the central moving average? I mentioned this yesterday. The central moving average is a non-causal filter. So if we look back at that formula, remember, if I had asked you at the 5th sampling interval to report a value, you couldn't say, well, okay, just hang on. I have my Ouija board here. I'm just going to predict what the future 5 samples are, and then I'm going to tell you based on the average of the 5 that I've seen and the next 5. I couldn't do that because I wouldn't know what the next 5 would be. And remember, I mentioned yesterday, causal filters in general are outperformed by non-causal filters, because it's a huge power. Everybody wants to see the future, right? And what we're doing here is we're using the future to make our prediction better, right? That filter is cheating. It's reporting at time 5 using the measurements at time 10. Is everybody following what I'm saying? A lot of people seem to be a bit confused about this idea, but I want you to understand the exercise. It goes like this. I have now declared it is time 1, right? And I've declared that the sample value is time 3. Okay? Now I've declared it is time 2. And I've declared that the sample value is time 5. Can anybody here calculate the 10-step moving average? No. Okay? Nobody can calculate the 10-step moving average because we don't have 10 steps. Okay? What about a 3-step moving average? By the time I get to time 3 and I put another 3 in there, at this point I am in the position to do a 2-step or a 3-step moving average, right? Now, at this point I can tell you that this value, it's 3.33, whatever. So that's the 3 time-step moving average. Now let's calculate the 3 time-step moving average using a central moving average for time step 3. How will we do that? Is anybody here saying, no, but I can't do it because I don't know what the value is at time 4? That's the point. And it's hard to imagine because I think so many of you have this experience of the data analysis that you do is always offline. Right? So you always do the experiment and then you analyze. But this is, remember, all of these online averages, the causal averages, are answering the question what can I do at the moment when I have that measurement available? but I don't yet have the next measurement, and I definitely don't have 10 measurements into the future, right? So it's not surprising that we can do better than the causal filters if we can effectively see the future, because at every time here, this filter is seeing the future. Now, also remember my advice. If you are doing offline analysis, you're a fool if you're doing causal filtering. Because why wouldn't you look into the future? Why wouldn't you use those values that you have available to you to get better results in the filter? So luckily that's very common. It's common enough that Pandas has that built in, so you simply pass center equals true into that rolling window. The way that this Pandas function works, by the way, allows you to do a lot of interesting things. You can do not only, like you can do aggregation by a lot of different functions. So I've used mean here, but like you can do rolling sums, you can do rolling standard deviations, you can do all kinds of stuff over windowed functions because you construct this windowed function and then you average it out. So basically you say, get that rolling window, and you see this doesn't actually have any values. That's just the idea of a 10-element rolling window over the data that you have. You can then do stuff like sum, and that will do a rolling sum. You can do mean, which is the one that we're doing now, and that'll give you the mean and so on. And you can kind of use, you can go and look in the docs at what aggregation functions are available. Right, and so predictably the central averages do a much better job at reconstructing the original signal. I want to call your attention to the problems that still remain, which is the 20 moving window. You can see that that's in a certain sense the smoothest of the responses, but the price that you pay for that is that you're getting a lot of things wrong. So you're responding a lot earlier than the actual signal to that input, right? You're also missing a lot of the overshoot on that response because you're kind of smoothing it out. And so the wider your window is, typically what you can imagine is that if your window size is of a certain width on time, you're going to start losing resolution on features that are that kind of size. So if you have so you can see that that's a 10-second space. That feature has that kind of shape, and on this kind of size, we're already losing that resolution. But it is the smoothest, and so we have to decide what's important. Like, do we want to get close to the original signal, or do we want to get rid of every piece of noise? Because here's a signal I'll give you for free: the ultimate noise-free signal, 0. Okay, 100% smooth, doesn't have any weird behavior, doesn't have any noise, never will make any trouble, definitely the wrong signal in most cases, right? So I'm saying that because that's the limit, right? Like if you really want to squeeze every bit of noise out of your signal, just turn the volume all the way down to 0. No noise. But filtering, therefore, is always this kind of trade-off between how much of the original signal I want to retain and how much of the noise I want to get out. And as I've mentioned before, like this kind of ideal brick wall filter that we think of when we think about the ideal anti-aliasing filter cannot be built. Every kind of filter design has a different trade-off. I'm not expecting you to be filter design experts. These filters are the ones that I really think that you should be aware of because they're the ones that are commonly used. And the next one that I'm going to do also includes so just to be clear, if you see smooth charts, definitely if you're looking at stuff like stocks, it's almost guaranteed that the smooth version that you're looking at is a moving average curve. Again, stocks are a good example of where if I want to know like what the average price is now, it's quite obvious that I can't use the stock price 10 days from now to do that calculation because that is not available to me, right? Wouldn't it be amazing if that was true? In our case, we are interested, so the moving averages are very widely used. I really, really recommend that you use central moving averages if you can. Exponential moving averages are interesting, not because they are good, but because they have a specific analog to first order filters. And so if you look at the derivation of the exponential moving average, which I'm going to go through now, you'll see that it is actually just exactly a first order filter. These first order filters, or these in exponentially moving, weighted moving averages terminology, it's parameterized by this parameter alpha. And we'll see what that means in a second. But as a kind of a rough guideline, basically what it means is the bigger alpha is, the more you're looking at the most recent value. And the smaller alpha is, the less you're looking at the most recent value, and the more you're looking at the average of the stuff that you've seen so far. And so small alphas correspond to aggressive filtering. Right, so small alphas correspond to large time constants. Okay, and we'll see that relationship in the, I'm going to do the derivation now. So that's basically how you implement this stuff in Pandas. It's kind of built in immediately. We can actually also write code that does this, but we just have to think about what those forms are going to look like. And I'm going to take you through what those forms look like now. So I want you to first focus on the Excel implementation that I showed you there. So if you just remember what this is doing, I feel that the spreadsheet is a really good analogy, because it's the thing that you guys are usually working with when you're using time series. If you're doing calculations, a lot of you have already got like a lot of mental space devoted to kind of imagining grids of cells like this. A couple of key things that I want you to notice is that this output cell, this moving average, was referring to that cell, that cell, that cell, and that cell, which are cells in the past, values of the measured signal in the past and now can be used to calculate values of the current output. And if we were to express that idea mathematically, I've used that sum operator now in Excel, but we could also have chosen to just say that y filter at time k is equal to ym at time k plus ym at time k minus 1 plus ym at time k minus 2, and so on until we get to 10, and then divide by 10. Okay, so that's the formula, that's the math behind this. And this idea, you'll remember that you've seen equations like this before when we spoke about difference equations, right? When we spoke about fitting linear, using linear fitting to fit the coefficients of difference equations, we saw models of this form. Now, remember that here, because we're thinking about the filter over here, we're saying that this is the filtered signal and this is the measured signal over here. And so here we've constructed a filter that is only a function of the inputs in the past. But, so that's what moving average filters look like. And I've written it in this way, but more commonly we would actually write it in this way. For 10 units. So what I want you to understand is that you can look at that and say, right, the current output is some weighted average or some sum of a coefficient times the values of the input signal in the past. Is this making sense to everybody? And we'll get to an interesting piece of math about this in a second, but I want you to kind of look at this form and see it has this linear form that we've been trained by now to recognize, right? So we've got a thing, and it's a coefficient times something, plus a coefficient times another thing, plus a coefficient times another thing. So it's kind of the same linear kind of shape that we are familiar with by now. Now, what about something like our trusty first order filter? Let me just make this bigger. So this is moving average. And if I wanted to get something that works a little bit like this, now remember the differential equation that arises from this would be, if we wrote this in the Laplace domain, this transfer function corresponds with the idea that yf of s over ym of s is equal to 1 over tau s plus 1. And if I kind of mentally work backwards from the idea, or let me just do a little bit of, I'm going to do this like longhand so that it's obvious, okay? So I'm going to cross multiply. I'm going to end up with yf of s times tau s plus 1 equals ym. And I'm going to multiply out yf of s times tau times s plus yf of s is equal to ym. And then I'm going to remind myself that in order to get this Laplace transform, I would have started out with a differential equation, right? So I would have started out with a differential equation that looked like this. Does everybody follow that piece of logic? Does everybody see that if I take that and I Laplace it, I end up with that equation at the top? Which means that if I inverse, and I want to just make sure that I'm using the right terminology. This is different from doing the inverse Laplace. Okay, because when you do the inverse Laplace of this equation, you'll get some equation of time. This is how we solve the Laplace transform, right? We're just reasoning backwards. Does that make sense? We're just saying, look, I want to know what the differential equations were that gave rise to that transfer function. I don't want to solve them. I want to figure out what we started with. So I'm kind of going backwards. I'm not inverting. I'm not doing the normal thing that we do with Laplace transforms, okay? So I reason backwards and I say, okay, that's the differential equation that I started out with, right? And then that means that I have this expression now in time, and I want to discretize this now. And just like we did when we talked about the discrete models when we were fitting them, we can say, let's approximate dyf dt, let's approximate that by yf k minus yf k minus 1 divided by delta t. So that's super, super, super important. 100% this is not an equality. Otherwise, calculus would be a lot easier. This is an approximation, right? So there are a couple of these different approximations. You may be aware there's like central differences. This is what is called a backward difference. Why are we using the backward difference? Because this is a causal approximation. In other words, it allows me to calculate the derivative now using information that is available now. Just like before, there are non-causal versions of this as well. Like you can approximate the tangent on a function much more easily if the whole thing is there than if you only have data up to that point and you're kind of forced to make a call, okay? So we do this, and when we do this, we now discretize. So this is like, this is called discretization. I approximate the derivative. I also express these things. So the derivative kind of approximates through this route. The other things approximate, and I say, well, when I used to say in continuous time yf t, I will now refer to yf k, the kth yf. And what I have now is effectively a discrete version of this equation. Now I can solve this equation for yf. because obviously I want to write this in the form where I have a formula, where I say, okay, so here's the filtered value, y if equals, and I solve that now, and I say y if k is equal to, and now I'm going to have to, well, let's do that longhand as well. So we're going to get a y of k minus delta t. I'm going to do it longhand, that's fine. So y of k minus y of k minus 1 plus delta t y of k equals delta t y mk. And then if I actually group all of those together, y of k times 1 plus delta t is equal to delta t y mk plus y if k minus 1. Check my algebra there. I'm really terrible at this kind of algebra, but like that should be okay, right?
You need a tower.
Where have I missed my tower? Oh, yes, there's a tower. Is that right? Check me. I missed the tower. So the key elements here are that we'll end up with, again, a coefficient times ymk plus a coefficient times y of k minus 1. And in this form, this is the exponentially weighted moving average. Now, basically what happens is that I have, in other words, the filtered value that I've calculated in the previous step, and I'm combining that with the measurement from the current step. And it turns out that these coefficients, you can go and check the derivation in the book, but these coefficients work out to be alpha and 1 minus alpha. So let me just quickly remind myself what way around that would be. So small alphas use mostly the old value. Yeah, so it's alpha 1 minus alpha. Okay, and that's the relationship between the time constant as well. But you basically can see that the first order filter has this discrete analog in the exponentially weighted moving average. And so everything that you know about first order responses, you also know about exponentially weighted moving averages. So there's two big take homes from this lecture today, right? The first one is, don't ever write these formulae yourself if you can help it, if there's a library function that does it, okay? Don't use, well, and I'll lump that in with the first take home, which is like, use the built-in functions, and like if you can, use non-causal filters. If you're doing math and you're trying to figure out how the math works, understand that the link between the continuous domain and the discrete domain, if we're trying to approximate the behavior of these continuous systems, this discrete approximation, this backward difference approximation, is one way that we can move from a continuous transfer function or a differential equation to a difference equation, right? And differential equations are to the Laplace domain as difference equations are to the discrete domain. They are the math that describes how things change over time.